All right, so this is going to be our second video on Chapter 9, differential equations. And what we're going to talk about are two specific types of differential equations. And they both involve exponential growth and or decay. So, the one differential equation that we kind of encountered a moment ago in the previous video was when we had dy dt equals y. In other words, when the derivative of a function gives us the function itself. Okay? And I claim that one function that we are familiar with that is the solution to this is our exponential function, some constant e to the t. Notice if you take the derivative here, dy dt, you rewrite your constant, and the derivative of e to the t is simply e to the t. So we are satisfied here, okay? Now, we can get a little bit more general, and we can say dy dt equals k times y. In other words, what we're saying is that the derivative is proportional to our original function. And I claim that the general solution to a differential equation of this form is c e to the kt. And I will tell you that c is actually our initial value. Okay? So, one differential equation that we're going to look at is going to be of the form dy dt equals k times y, and the general solution is c e to the kt. Okay? If you don't believe me, take the derivative of this and you can verify the solution. You can verify that we're going to, on both sides, get ck e to the kt. Okay? So, this is one type of differential equation we're going to look at. How do we know when we're looking at a differential equation of this type? What we're saying is that the rate of change is proportional to the original function. Okay? So, what if I want us to find the general solution for, how about dy dt equals negative 8y? Well, y, notice the number in front of your function is what the k is in your exponential. So it would just be c e to the negative 8t. Now, I could give you a further piece of information. What if I say, hey, when t equals 0, c is 100? Or excuse me, y is 100. Okay? This is another one of those initial values. Well, we can plug this in. We could say 100 is c e to the 0 power. Notice that just gives us c is 100. Sorry about my little foreshadowing a little bit ago. So in here we would say our particular solution is c e to the negative 8t. So in a differential equation of this type, this is our initial value. Okay? So what if I told you this? What if I said dp dt equals 0.15p, and suppose p equals 10 when t equals 0? Notice we can get our function p. Well, we know our initial condition. We know our initial value is 10 e to the 0.15t. Okay, so what if we want to take this example? What if I tell you that a radioactive isotope decays at a continuous rate of 25% per day? Can we write a differential equation as well as give the general solution? And I claim the answer is yes. So to write the differential equation, doesn't really matter what letter we use. We'll say dA dt. Okay, notice it's decaying at a rate of 25%. So we have negative 0.25a. All right, well, what is my general solution then? A equals C e to the negative 0.25t. All right, well, let's do a couple more examples of this kind. What if I tell you that a country experiences a continuous inflation rate of 5.2% per year? And what if I want us first to write a differential equation for V, the value of an item after T years? I'll get more specific with T momentarily. All right, well, dV dt, we know the rate is 0.052 and it's 5.2% of the value. Okay, what if now I want us to give a general solution? Okay, well, that would be V is C e to the 0.052t. And finally, let's just assume a t-shirt had a value of $10 in 1995. And we want to know, what would you expect the value to be in the year 2020? And let's assume that t equals 0 corresponds to the year 1995. All right, well, what are we going to do here? What we're going to do is just expound upon our general solution. Notice if t is equals 0 corresponds to 1995, then I know a particular solution here is 10 e to the 0.052 times t. And if t equals 0 corresponds to the year 1995, let's assume then t is the number of years since 1995. Okay? So what we want to know is, what would the value be in 2020? Well, how many years after 1995 is 2020? Claim that's 25 years later. So all we would do is plug in 25 here. So let's see what we get. 0.052 times 25. Wow, we would expect this shirt to be $36.69. All right, let's do one more example of this sort. What if I gave you this? Consider the population of a region where there is no immigration nor emigration. The rate at which the population grows is proportional to the size of the population. That already tells us that we're in this form. So the rate of growth is proportional to the population. Okay? And let's suppose that it grows at a continuous rate of 2% per year. Well, if I asked us to write a differential equation, dp dt, I claim we know that's 0.02 times p. Okay? So when you're given that the rate of growth or decay is proportional to, you know you're in this form. Now, further suppose, what if I told you that the initial population is 2,000? And I want to know, when will the population reach 5,000? All right, well, we have our general differential equation. Notice we're given our initial population, that gives us our C. So we have 2,000 times e to the 0.02t. And now what we want to know is, when will it reach 5,000? Notice we're given a value of p, and we want to know when, therefore we want to find t. So we can certainly solve that. 5,000 is 2,000 e to the 0.02t. Well, isolate your exponential, divide both sides by 2,000. You're going to get 5 halves is e to the 0.02t. And how do we get to our exponent? We take the natural log of both sides. So we have the natural log of 5 halves, and we know that the natural log of e raised to a power is just that power, since they're inverse functions. So to get t alone, we can divide both sides by 0.02, and I claim you're going to get t to be in about 45.8 years. All right, so that is one type of differential equation that we're going to be we've talked about. Now there's another one that we've already alluded to, going back to our YAM example. Okay? The other type of differential equation that we're going to look at is when you're given that dy dt is equal to k times y minus some value of a. Okay? Both k and a are constants. So this should ring back to that YAM example where we had k, and I believe it was 200 minus a. Okay? Well, I claim that the general solution for this differential equation is a plus c e to the kt. Okay? Now, we can verify that this is a solution. Again, we can verify this in much the same way that we verified in our last video. Okay, so how would we verify this? Well, notice we would take the derivative of this. So this is just a side note, but I think it's an important thing for me to point out. Okay, so Just to verify, as a side note, we can take dy dt. If that's our function y, the derivative of any constant is 0. And we've taken the derivative of that before, ck e to the kt. So that's the left-hand side of my differential equation. Now what I'm going to do is show you the right-hand side. Notice that's k. Now y minus a. Well, y is a plus c e to the kt. Subtract off a. Those a's cancel, and we get the same thing. So what I've now shown you is that I am not a liar when I tell you that this is a solution to this differential equation. Okay? Now, how do you know when you're encountering this sort of differential equation? We saw here that it was proportional to that function. Here, what you're going to have is you're going to have it be proportional to the difference between two things. Or another way you could have it be worded to you is that, like with that bank account, something's increasing and it's decreasing. Okay? So let's just practice with this form because not everything is always given to us in that nice a form. For example, what I want us to do is give the solution to, well, what if I say dy dt is 0.5 times y minus 100? Well, let's translate. Y equals, notice that's my a, 100 plus c e to the 0.5 t. And that's all we can do with that. Okay? Now let's give the solution to this guy. What if now I tell you dp dt is negative 0.8p plus 160? So this one would have been given to us in so many words that it's decaying at a continuous rate of 80%. And it's increasing at a constant rate of 160. Okay? Now, I claim we're in this form. We just have to do a little bit of algebra to get it written this way. What do we need to do? Well, in order to get it into the above form, what we need to do is pull out the number in front of our p. So negative 0.8, if I factor that out, I'm left with a p in my first term. And if you take 160 divided by negative 0.8, you're going to get negative 200. So, what's my general solution? My general solution is 200 plus c e to the negative 0.8 t. All right. Let's just do a couple more. What if now I tell you dB dt plus 2b equals 50. And I'm also going to tell you that b of 0 is 100. So the first thing that we're going to do is get this differential equation in a form where we can write the solution. And this one is another initial value question. Notice that we're given our initial value here, that when t is equal to 0, b, whatever b is 100. Okay? So how do I get this to look like over there? First thing I'm going to do is scoot my 2b over. So dB dt is negative 2b plus 50. And then my next step again is to factor out the negative 2. Claim we're left with b minus 25. So my solution is 25 plus c e to the negative 2t. Okay? Now, notice we're given another piece of information, and this other piece of information is actually going to allow us to solve for our value of c. Now, we saw over here in this sort of differential equation that c was my initial condition. That's not the case here. Okay? So, what can we do? We know that 100 is 25 plus c times e to the 0 power. Therefore, I claim c is 75. Therefore, in this particular case, my particular solution is 25 plus 75 e to the negative 2t. Okay, so here we are. Now, I would like to do a couple more examples of this sort. Okay? These are going to be more of a word problem type. So what if I told you that a person receives a drug intravenously at a rate, so receives the drug at a rate of 0.5 milligrams per hour. Notice it's not a percentage, that's our constant. And then we're given that the drug is metabolized and leaves the body at a continuous rate of 2% per hour. Let's first write a differential equation for the quantity of the drug present at time t. Now we've got two things going on here, right? There's a drug going in at a constant rate, so that's going to be positive. And then it's going out at the continuous rate of 2% of the amount present. Okay? Now, what if I want us now to give the general solution to this differential equation? So, if now I want us to give the general solution, we have to do a little bit of algebra here. Okay? Again, we have to get it into this form. So the first thing that we can do is say dq dt. We can first rewrite it so that our constant, so that our term with the function is first. Now what we can do is factor out a negative 0.2. Well, we're left with a q in this term, and 0.5 over negative 0.02 is a minus 25. So my general solution is 25 plus c e to the negative 0.02 t. Alrighty, so let us do one more example. And this next example is just a really common way we look at this last differential equation. Now you may have heard of Newton's law of heating and cooling, but that's essentially what we're going to look at here, okay? Newton's law of heating and cooling says the temperature of a hot object decreases at a rate proportional to the difference between its temperature and that of its surroundings. Similarly, the temperature of a cold object increases at a rate proportional to the difference between its temperature and the temperature of its surroundings. I mean, for example, think about a bowl of hot soup, okay? Clearly the temperature cools off in a room, okay? At first, the difference between the temperature of the soup and its surrounding is great, so it's going to cool off fast. But as time goes on, the rate at which it cools slows down. Okay? So this is a really, really common way to look at this sort of differential equation. So let's just talk about one more example. What if I tell you that a bottle of juice at room temperature, so we'll just pretend that's 72 degrees, is placed in a refrigerator whose temperature is 44 degrees. And I'll tell you that after a half hour, the juice has cooled to 61 degrees Fahrenheit. And we're going to assume T stands for the time in minutes. Okay? So the first thing that we're going to do is write a differential equation for this. Okay? So we'll call it dJ dt, temperature of the juice at time t. Well, what do we know? We know by Newton's law, in this case of cooling, that the juice is going to cool at a rate proportional to the difference between its temperature and the temperature of its surroundings, which is 44. So at this point, we can get our function j to be equal to 44 plus c e to the kt. Now, notice we're given some more information. What is one piece of information that we're given? We're given that initially, in other words, when t equals 0, my juice is 72. Well, that's going to give us c. Let's check it out. 72 is 44 plus c e to the k times 0. So we get 72 is 44 plus c. And we can solve for c by subtracting 44 from both sides. We're going to get c to be 28. So now we have a differential equation of the form 44 plus 28 e to the kt. Now, we're also given another piece of information. We're also told that after a half hour, the juice is cooled to 61 degrees. Okay? This last piece of information is actually going to give us the value of k. What do we know? We know that the juice is 61 when t equals 30. Notice t is in minutes. All right, well, what can we do to solve this? First thing we do is subtract 44 from both sides. So we're going to get 17 is 28 e to the 30k. My next step is to isolate my exponential, divide both sides by 28. So I'm going to get about 0.6071 is e to the 30k. And last but not least, I'm going to take the natural log of both sides. So the natural log of 0.6071 is 30k. And we divide both sides by 30. I claim if you do that, you're going to get k to be negative 0.02. So my juice is 44 plus 28 e to the negative 0.02 t. Okay? Does it make sense that our value of k was negative? Absolutely. It makes sense precisely because this juice is presumably cooling off. Well, now that we've done all of that work, let's just ask ourselves, When will the temperature be 50 degrees? Okay, so when will J be equal to 50 degrees? And again, this is just solving another exponential. We have 50 is 44 plus 28 e to the negative 0.02t. To solve for t, first subtract 44 from both sides. So we get 6 is 28 e to the negative 0.02t. Next step, isolate your exponential, so divide both sides by 28. We're going to get about 0.2143 is e to the negative 0.02t. What's my next step? We take the natural log of both sides. And that'll give us the natural log of 0.2143 is negative 0.02t. And then divide both sides by negative 0.02. And you're going to get t to be 77. So we can say after 77 minutes. Isn't that cool? All right. Thank you. I hope this was helpful.